Today I'd like you guys to start working on a new equation and a new concept called the photoelectric effect, and the equation is for photon energy. Because I'm not here to walk you through this, I'm going to put together a short video here so you can see what this equation is and how it's used. I would like you to, on your own, read through this top section and answer the questions that follow on the bottom of the first page, the first two. We'll talk a little bit more about this tomorrow in class together, but I would like you to at least read this and try to answer the first two questions. The other part that's in here is the equation down here for the energy of a photon. An individual particle of light is called a photon, and it has a certain energy that's based on its frequency and also its wavelength, since those two are related. So this equation tells us that the energy contained in a photon is equal to h times f, or hc divided by the wavelength, where the constant h is Planck's constant and always equal to this number down here, 6.23 times 10 to the minus 34. It's an incredibly small number, is Planck's constant, but you'll need it to calculate energy in these equations. C, listed over here, is still the speed of light, 3.0 times 10 to the 8 meters per second. That is also a constant for these equations. So really, all you're doing is taking either an energy and turning it into a frequency or a wavelength, or you're taking a known frequency or wavelength and turning it back into an energy. So let's try one together. On the back side, question 3 asks you to figure out the energy in a photon if we have a wavelength of 445 nanometers. So what that's asking us to do is solve, obviously here for the energy, that's our question mark. The wavelength of light is given to us as 445 nanometers, so I'm going to go ahead and write that down, 445 nanometers. Nano means billionth, 10 to the minus 9, so since our constant for velocity and Planck's constant are both expressed in terms of standard units like meters, we're going to convert that into meters. And this is relatively simple. From nanometers into meters, we just multiply by 10 to the minus 9. So this is really equal to 445 times 10 to the minus 9 meter. And of course, we still have Planck's constant, always 6.23 times 10 to the minus 34. The unit here is joule seconds. And because we've got a wavelength, it also may help us to write down the velocity of light, 3 times 10 to the 8th meters per second. To solve this, we're simply going to take our energy equation. We don't, for this problem, need the HF version because we don't have a frequency. What we have is a wavelength. So the energy here is equal to hc over the wavelength. So I'm going to put that in over here. The energy in our photon is hc over the wavelength, where h is 6.23 times 10 to the minus 34. C is 3.0 times 10 to the 8th. And the wavelength is 445 times 10 to the minus 9. Because of the amount of scientific notations involved in this calculation, you do want to be sure that you're being deliberate about where your parentheses go. In fact, I didn't write them in here, but if you're doing this on a calculator, you certainly want to have that last one enclosed in parentheses. When you calculate this number out, you should get something relatively small, somewhere on the order of 4 times 2 times 10 to the minus 19 joules. And that is the energy contained in a single photon of light with a wavelength equal to 445 nanometers. Use that example and the equation to figure out how to solve the rest of your problems here. And if you have any questions about these, I'll be available tomorrow to answer them for you.